Hey everybody, this is Larry. This is June 23rd, the 23rd day of the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button. Let's get started on hitting the refresh button. And also join the Discord channel if you want to hang out, talk about this problem or other problems or anything. And also waiting for the refresh to stop, to finish loading. A lot of technical difficulties recently. Okay, there we go. Count complete tree nodes. Let's see. Count complete tree nodes. Given a complete binary tree, count the number of nodes. What is a complete binary tree? In a complete binary tree, every level except for possibly the last is completely filled. And all the nodes in the last level are as far left as possible. You can have between 1 to 2 to the h nodes inclusive at the last level. Okay. So you can definitely do this depth first search in linear time by just counting the number of nodes by running depth first search, and that'll work for every tree, right? Every tree, every node. What I'm thinking about is, can we do better? And I think probably. So, is there a greedy way, right? So basically, the largest number in this tree, and it's not a binary search tree, it's just a tree that is essentially a heap, right? But given that it's complete, it's always going to be full if let's see. So I'm just thinking about the different cases, right? Can you do greedy? I'm not quite sure that you can do the greedy, because for example, if this has 5 nodes, then if you try to go to the right, it would go to the 3, and then on the left you still have, the rightmost tree and the 5. So but I think this is a good case to test, is that 5 nodes and the 6 nodes, because then you're trying to do some math around the right and the left, right? So, can you do it better than the linear time? You're not given the depth either, and the problem is that you're not. Can you figure out the depth of a tree without looking at both the left and the right side? So one invariant that you find about this problem is that there is an invariant about this problem. The invariant about the complete binary tree is that the left subtree and the right subtree, the right subtree is the depth of the right subtree is the same as the depth of the left subtree, or it is the depth of the left subtree minus 1, right? Is that good enough for us to figure out? But well, then we could, in that case, then the max depth, so the actual depth is just because of that invariant that we talked about, then the left subtree will always be, if you just keep on going left, you will find the depth of the tree, right? So then now, given that, is that enough to solve? I think so. I think now, no, is it? I think the 6 is always the interesting case. So, because I was thinking maybe I could just keep on going right. Right? Okay, so I think I have a recurrence here, actually. Now that I think about it, right? Okay, if the left subtree is equal to the right subtree, so you can calculate your depth in 2 directions. Well, they're not really the depth then. It's just you look at the depth going left, going all the way left from a current node, and then you look at the depth going all the way to the right node, right? And this gives you a bit of information. And that bit of information is that if they're equal, that means you have I forget what it's called, but it's a full tree essentially, and then that means that that tree is full. If it is not, then you go to your left No, wait, do you? Maybe not. This is a really annoying problem. I don't know if I'm supposed to be able to do it with O of H, but because I think the sixth case is also the case where, okay, if you go left, like, okay, in this case the depth is the same, but it's, you still want to go right. But you know that left is not good, or that, so basically you're trying to find the first complete subtree on the left, and then you kind of keep doing that, but I'm not convinced that that would be, that would give us better than O of H. I think that's my problem. Maybe it could even be O of H squared, which is log of n, so log square n maybe. But but basically at 1, if you go all the way left, okay, maybe I have, maybe I need to rethink that a little bit, and maybe that's okay. Which is that if you go all the way left, and then you go to the right, and then go all the way left, if it is the same depth, that means that, what does that mean, right? That means that, well, that means that with the 6, that means that all the 5s are true, like all the cousins of the tree, which is to the left, is true, and that your answer is to the right of, it's on the right subtree, right? So that means that it will be 5 times oh sorry, 5 plus the number of nodes on the right, something like that. And then you just try to find this first subtree. So basically you just find the node one at a time, the first node in which if you, the leftist node and then the right leftist node has different value. Because when that is the case, on the lowest case, then that is your number of nodes. I'm not sure that that's better than O of n though, to be honest. We might have to do some math to analyze the complexity afterwards, but I think maybe that should be good enough for us to get started. Yeah, let's kind of do that. So we count the depth of the subtree. Okay, yeah, okay, let's do that. Let's depth of a subtree node, and right now the complexity is going to be a little bit messy. We'll talk about ways to fix that complexity in a bit. But yeah, if node is none, return 0. If node, okay, if node is a value, then return depth of node plus 1. Whoops, depth of node dot left plus 1. Right. And then we can just memorize this, spoiler alert, but right now we could save the memorization later. And then now we look at each node. Really not convinced that this is better than O of n, but okay. So now okay, so if root is none, then we return 0. Otherwise, left depth is equal to depth of root dot left. Right depth is equal to depth of root dot right. And then if they're equal, what does that mean? If they're equal, then that means that we want to traverse to the right side. right? If left is tab is equal to right tab, then we want to do something like count nodes. We might have to play around with this formula. I'm not convinced that this is right, but well, I think this is more mathematical, which is I might do a helper instead. But oh yeah, then it's just left depth. Okay, so if they are the same depth, then we know that the left subtree is all full. So that means that there are on the left subtree. Let's see, this one. It's just 2 to the n minus 1, right? 2 to the depth minus 1. So yeah. And I know that you could do bitwise, but I like doing it this way. So it's, and then you add the 1 for the root node, and then you just add the count node of so you minus 1 and then plus 1, and then you add the count nodes of root dot right. If or else, if they're not equal, what does that mean? If they're not equal, then that means that you want to go left, right? That means that you want to go left. Plus, how many nodes are on the right side? Well, it's just 2 to the right depth, and again you count the root, so you minus 1 plus 1. Okay, to be honest, right now I'm not confident about this, but let's play around with it. Okay, I have to declare this as self dot count node. Okay, is this just literally return a full tree? Okay, fine. Let's play around with all the, let's just be exhaustive about the first couple of answers, because these are easy to visualize mentally, like what the right answers are, right? Okay, so that looks okay. Let's see. So the thing that I said earlier is that every time you do a count node, it calls a depth, and you could kind of see that in this depth case, that you call it for the same node because this is recursive. You call it for the same node multiple times, so we can actually cache this. We can just cache this, right? And this is why I do it recursively. But let's just say we have a cache is equal to yeah, just a dictionary. It's fine. If node is none, return 0. If node in cache, return cache of node. Otherwise, result is equal to this. Oh, actually, let's just do cache of node is equal to this, and then return cache of node. I guess you could also rewrite it this way. It's a little bit clearer. All right. Oh, it's self.cache. Did I miss the place? Does this not get called? I forgot how to set members variable here, but okay, fine. I mean, you could do it different ways. I just think about which way is the cleanest. They're all kind of a little bit messy. Oh, wait, no, I just forgot here. maybe. Okay, so that works. That's what I thought, but okay, fine. Let's just try one more with the, oops, 8, 9. So yeah, so you know that this only gets called once at most for each node, so this is of n for the number of nodes at most, but let's kind of click on submit button. So this works. How do I feel about it? So this is definitely not the standard. So you can definitely do the standard depth first search and count the number of nodes, and then you could do that O of n times. Let's kind of analyze our complexity now, right? Which is that, okay, in this case, this is at most O of n, but that's just the number of nodes that are visited. So this looks at the left subtree and then the right subtree. Actually, where the h is the, so each core is h, right? Yeah, so for, okay, so I think I have the complexity, which is kind of a little bit confusing, but, and maybe I'm wrong on this one, but basically, okay, you have h, right? So for each depth in h, we only call it once, right? We call this count node function once. So that means that where h, so we only call count nodes h times, where h is the height of the tree. And for each height, how much work do we do? Well, we call it depth on the left and on the right. So, and this does at most, this does O of h times initially, right? For each node. So that's to the left. It's going to do O of h operations. And then to the right also does O of h operations based on height. So it's going to do O of 2h work. Some of this is cached, so it's not quite, it makes the complexity a little bit trickier. But because you branch out, it's not going to cache all the time. So it's going to be still O of h, because it's going to miss cache O of h times, right? So the caching actually didn't do much, but maybe okay. Because from that, we know that because h is the number of possible inputs, and each input does O of h work in counting the depth, this entire algorithm takes O of h squared times. And because h in this case is exactly O of log n, that means that this algorithm is log n square, or log square n, sorry, because they're different. Yeah, and in terms of space complexity, it is probably O of h, because it does h square as well, because yeah, because it does h on the first iteration and then another h, or h minus 1 on the second iteration, so forth, in terms of space. So it grows h square, which is also log square of n. So that's the running time complexity of this problem and algorithm. Let me know what you think about this problem. It's probably very easy to do it in linear time, obviously, but definitely see if you could do this divide and conquer. It's kind of really tricky to get right. I think this complexity is, the complexity analysis is really hard in general to get precise. Still not that confident about it, but the algorithm is something that is also kind of cool and kind of cute. I didn't really think about it. Yeah. In terms of an interview, I would say that this is probably a little bit on the harder side, but it's still within scope in the sense that this is just depth first search plus a little bit of divide and conquer, and making one big observation about how to count the depth of a subtree. And in theory, you should have all the pieces that you need for this puzzle, for this problem, for this interview question, right? It's a little bit tricky getting them together, so that's why I said maybe. And you definitely need a couple of observations to make this work. So it's a little bit tricky for an interview, but I could see that it being an interview question. For competitive programming, this is really cute and really interesting. I don't know how they could ask this as a competitive, because if they give you the tree, then just reading everything, it's going to be linear time. But it's cute. I like to practice, and the tricky part is just thinking about how to do the divide and conquer. And once you do that, everything follows for a little bit. This is actually the first time I think I've seen this problem, because, like I said, in competitive programming, it's very rare to get these kind of problems, because it's very hard to give the input in a way that makes sense. But so for me, everything that you watch, I kind of had to figure out live and prove live. So let me know what you think. Hit the like button, hit the subscribe button. That's all I have for this problem, and I will see y'all tomorrow. Bye bye.